As discussed previously, transistors are the most basic elements of digital circuits and systems. So transistors basically work as switches, and these switches can be used to represent digital signals. The most common building blocks in digital systems are gates, or more specifically, logic gates. So there are three basic gates using which you can construct most digital systems. Basically, all the digital systems you find today are constructed using the three basic gates. The first gate is the AND gate. So this is the circuit level description of an AND gate. It is just for your understanding. So let's say I have a battery here. It's connected to the ground. This is my switch A. This is switch B. So right now both my switches are off. Basically, switch is off indicates that it's like this, and a switch on indicates that it's like this. At the end of the two switches, I have a bulb which glows. It can be an LED or any other bulb. And I close the circuit. Now, what are the conditions of switch A and switch B for the bulb to glow? So A, B, let's say the bulb is F. Now, there are four different combinations in which switch A and switch B can be positioned. The first combination is switch A is on. The first combination is both switches are off. The second combination is switch A is off but switch B is on. The third combination is switch A is on but B is off. And the last combination is both my switches are on. So for which combination do you think the bulb will glow? So for what combination of A and B will my bulb glow? Bulb glowing in the sense, one is bulb is on and 0 is bulb off. So when both my switches are off, there is no way that the current is going into the bulb, which means that my bulb is off. Now when switch A is off and switch B is on, the current is not going to go through because switch A is off. Therefore, my current does not reach my bulb, so it still doesn't glow. Same thing happens when switch A is on and switch B is off. The current passes through switch A, but it gets blocked by switch B. Therefore, no current goes through the bulb. Therefore, it's off. And then finally, when both my switches are on, that is when my circuit is complete and my bulb glows. So this is the truth table. So this operation is nothing but the operation of an AND gate, and it is represented as so this is the gate. A and B are the inputs to the gate and F is the output to the gate. Now F is asserted, that is the output of the AND gate is asserted when both A and B are asserted. That is for this combination here. So this is the symbol representation of the gate, and the mathematical description is F equals A and B. Some people also write F equals A and B. They do not include the dot, but it's implied. And some people write F equals to A and B. I typically use one of these two, They are interchangeable, that's no problem. And A and B, this is used in VHDL programming. We're going to deal with that later, but throughout the course, when I mean AB, it means A and B. The second gate is the OR gate. So let's look at the high-level description of the OR gate. So you have a battery here, which is connected to the ground. This is switch A. This is switch B. And here's my bulb, F, and I connect it back to the ground. Again, similar to your AND gate, there are 4 combinations. So both switches can be off, one of them can be on, and the other one can be off, and both switches are on. So for what combinations of A and B do you think the bulb will glow? So if both my switches are off, then the current is not going to go through any of the switches and it's not going to reach the bulb. So the bulb remains off. When at least one of the switches is open, let's say in this case switch B is open or switch B is on, then my current is going to go through this direction here and it reaches the bulb. So it's going to be 1. The same thing happens when switch A is on but switch B is off. In that case, current will directly go from here all the way to the bulb. So that's the bulb is on. And when both the switches are on, the current goes through both of them and it's going to come out of here and reach the bulb. So that's 1. So for an OR gate, if at least one of the inputs is 1, then your output is a 1. So the symbol for the OR gate is so if at least one of the input is asserted, the output is asserted. The mathematical description of the OR gate is F equals A or B. And some people write F equals A or B, but I'm going to use this notation. The final gate that we are going to deal with is the NOT gate. It's also known as the inverter. So what a NOT gate does is, you have an input A. This is the symbol of the NOT gate. And you have F. So the truth table is A can take either 0 or a 1. So when A is a 0, your NOT gate is going to flip the input. So if A is 0, your output is 1. And if your A is 1, your output is 0. And they typically write F equals not A. Some people use A bar. Some people use A prime. I typically use these two. So using these 3 gates, all modern digital systems are designed. The most complex processor is going to contain these 3 gates. There are other gates as well, but those gates can be constructed using these 3 gates.